Welcome back to PC1 for the final update of 2025 before we take a short Christmas break. This year has been very much a year of coming of age for the company, where delivering our big ideas boils down to sweating thousands of vital little details. The team have diligently delivered just that, and now we're ready to pull all of these individual pieces together to finally build this great big jigsaw. Here's an update from across the programme of where we're up to and what to expect in 2026. Let's start with the GT50. Let's start right at the front of the engine with the GT50 centrifugal compressor. This is the very first titanium GT50 impeller wheel. It's made from the right material. We've had to develop all of the heat treatment processes to get it up to the right strength and condition for use in the engine. Then we've had to develop all the jigs and fixturing and everything else that we need to do to get it on the machine. Develop all of the cutting strategies to get the geometry and also the surface finish right as it comes out of the machine. All of that's been done. It's been taken through the inspection process, and we're just finalizing the last few corrections to get the geometry just where it needs to be for that to be ready to go on the test engine. The very next step is, once we're finished on here, it's off to be assembled to the rest of the first GT50 rotor, and that will go off to be high-speed balanced, ready to run smoothly in the engine. So in order to trap the pressure in the individual passages of the centrifugal compressor, it has to run up against a shroud. So that's essentially just a part of the housing that runs really, really close up against the tip of the individual blades. Now, because that clearance has to be held to less than 0.2 millimeters, it's really important that, should it ever rub, it can't create a titanium fire. So what we do to allow us to simultaneously achieve the tight clearances and have that margin of safety is to use an abradable coating that is a sort of sacrificial coating if ever there was a rub for whatever reason. So you saw us report a little while ago that the shroud, which is the forward part of the casing there that the compressor runs in, had been machined by Mick over on the big lathe, and then we've subsequently had a batch of 5 of these components have the abradable coating applied to them. So the compressor, it actually runs that way round in the engine, and the compressor sits in there. So the inlet is on this side and this is the outlet. The compressor sits in there, and then we machine back this abradable coating to give that super tight tolerance, that really good surface finish, and the protection that the titanium impeller requires. So we've got 5 of these in stock now that allow us to tune that fitting and build multiple engines. Next, we can talk about the GT50 combustion system. So the combustion system is the most part of the gas generator module of the engine. So we have the combustor casing, inside which is the combustor liner. At the back of that, we have the fuel manifolds, which are fed by the individual fuel lines, and this common rail fuel line is connected directly round to the fuel control valve that sets the pressure in there. So in order to produce all of this stuff, we've got a cast combustion casing, which provides all of the bosses and manifolds for the fuel manifolds and for the service pipes and the various other bits of instrumentation and kit we need on there. And then within that lives the combustion liner that we've shown you all previously. So a lot of time and effort has gone into producing this. And where we are with this currently, as we've shown you, is we're now producing both the inner rings that form the inside part of that here, and also the larger outer rolled rings perfectly. So these have got all of the correct form, they fit together beautifully, the welding quality is perfect, all of those are ready for the prototype engine. Over the last few weeks, the guys have now been putting some effort and energy into these end rings here that direct the flow round the corner and back into the nozzle guide vane. These particular parts of the combustor have to be pressed, and developing these deep drawn pressings is quite a task. Let's go and have a look at how the guys have been dealing with that. In order to make those highly curved sections of the combustor, we need to take a flat piece of material like that and then press it until it takes up a form like that. And the challenge with that is as the material is fed in between the male and female parts of the press tools, there's a tendency for the material to pucker and to sort of wrinkle up like this, which doesn't conform to the design intent. So in order to optimize this process, we've been using the very same technology that we use to design your crash-worthy structures on the fuselage itself to simulate the way that the metal flows in between the press tools under these extreme pressures. So Katie's been doing a bunch of simulations to optimize the design of the press tools, optimize the correct material thickness to start with, so that once we've pressed it, we've got enough stability in the thin walls of the material for it to not buckle and for it to keep nice and straight, to give us enough undeformed material so when we cut this off, a lot of this here is scrap. When we cut this off to get just the bit that ends up being welded to the rest of the combustor, we've got just the right form for the design intent. The combustion casing is really the enclosure for the whole combustion system. We attach the manifolds, the service pipes to that, and it supports the combustion liner. The combustion liner that I've just shown you is the flame holder, if you like. That contains all of the combustion processes, but to make that work, we also have to get the fuel into the system. Now, you've seen us chart the process of developing our advanced fuel nozzles over the course of the last few months, really. And what we're doing now is we're testing a wide range of nozzles here on the flow rig, and also on the aquarium, and also on the Rufus Ron test rig. So the work that's going on here is enabling us to qualify the level of atomization that we're getting from the nozzles at the wide range of fuel pressures that we need to be able to modulate the fuel flow from ignition through ground idle, flight idle, all the way through the power range, to make sure we can control the engine and have a stable and reliable flame throughout the entire operating range. So the parameters that we're trying to optimize here before they go on to full engine testing is the fuel scheduling that we need, the exact orifice sizes that we need for the fuel nozzles, and then little nuanced details like the exact position of the igniter relative to the fuel spray cone. All of those things really need to be established experimentally, and it's much easier to do it on a test rig like this than on the full gas generator test. So lots of testing been going on over the last couple of weeks or so to qualify the fuel nozzles. We're then going to be moving on to extending this testing to allow us to move the spark plugs around, vary the operating conditions, and verify the way that we can cross-light from one nozzle to another around the 12 nozzles that we've got on the combustion casing, because obviously we've got 12 nozzles but only 2 igniters, and so each nozzle has to cross-light its neighbour, and proving that we can do that reliably in all of the operating conditions we need to is one of the things that we're working on here, initially with Rufus 1, and then as we develop the Rufus 3 rig to give us the confidence that we need that we'll have trouble-free starting on the full engine test. Once the air comes out of the compressor, it then goes into the vaned diffuser, which recovers about another 50% of the pressure rise that the whole compressor system has to generate to feed the combustion system. So to make this component, which is essentially a ring of vane-shaped passages between 2 tightly packed walls, for the prototype engine, we're essentially hogging this out of solid. In practice, we'll cast those, but for the first engine where we might want to change things, we're just machining that. So this billet here is destined to go onto the 3-axis machine, onto the lathe, and then the 3-axis machine to have the passages hogged out and then the vanes machined into it. We use the large outer portion for the large front end of the diffuser. This inner section is the back part of the diffuser where it connects to the nozzle guide vane, and then this centerpiece that would otherwise be waste is what we use to create the tensile test pieces that allow us to validate the material that go into the diffuser. So once we've produced all of that hot gas in the combustor, we've then got to turn it so it strikes the turbine blades at the right angle and velocity. That's what the nozzle guide vanes do. These are cast rings of superalloy material that hold all of these blades, and then we EDM out the slots to be able to cool them and keep this thing protected from the ferocious temperatures that we see in the engine. We've now developed all of the casting processes that we need to manufacture these nozzle guide vanes in one piece, in the correct material, and fully fill them. So this is now fully conforming from a casting point of view. We're doing the last bits of inspection and geometry correction, so just pre-warping this for how it shrinks and distorts during the solidification process, so it ends up back at the right shape. And then once we've done that, off to heat treatment, and then onto the EDM machine to use the processes that we've shown you previously to cut those cooling passages. And then that too is ready for test. Moving back from the combustor then into the turbine, there's two major elements, the turbine disc itself and then the turbine blades. If we start with the turbine disc, over the last couple of weeks you've watched us reporting the early stages of machining of the disc out of the high integrity superalloy material on the Multus machine. Those components are now in here in metrology, and what we've got on the CMM machine here is the first example of the second operation on the disc. So when we first turn it over and machine the other side. So this is the Curvix, and then the bigger labyrinth seal, and then the back side of the cob, which is where we cut out the female version of the fir tree to support all of the turbine blades. Ollie's just proving out the first elements of this CMM program. The early inspection reports that he's got on the screen over there all look pretty good. We look like that we're pretty much in tolerance with everything at the moment. And then once we've done that, the next stage is to move on to this process where we take a turbine disc that's had op 1 and 2 done on it, and then we can get it set up for cutting out the female part of the fir trees that will slide and support all of the turbine blades. We've reported extensively on the development of our investment casting processes for casting superalloy turbine blades for the GT50 engine, taking wax patterns, creating the shells we need to then create cast trees of both HP and LP turbine blades in nickel-based superalloy materials. In order to do this, we've had to develop all of the casting processes, then adjust for all the shrinkage and distortion that happens during solidification. And then the final stage of that has been to take these blades and get them heat treated so that we essentially take a collection of separate elemental metals that solidify at different rates as the material cools, and create the proper alloyed crystal structure that we need to deliver the mechanical properties that are essential for safe operation within the engine. Over the period of the last couple of weeks, now that we've got the basic casting process working and all of the infrastructure in place to be able to deliver that, the guys have been doing all of the development on the heat treatment and then the mechanical testing that qualifies the mechanical properties that are delivered by our cast materials in our turbine blades. Over the course of the last week or so, we've had the first wave of test results back that demonstrate that our turbine blades are meeting or exceeding significantly in some areas the mechanical properties that we've assumed during mechanical design. What that means is our casting processes work, our heat treatment processes work, and we're now delivering cast turbine blades that are strong enough and have high enough integrity to work within the GT50 engine. So last time I opened one of these boxes for you, it was full of pipes, but this time we've now got a full set of HP turbine blades for GT50. So these are the gas generator turbine blades. These ones have been finished machined now. They've had the fir tree roots ground onto them, and these are the ones that we'll most likely use for the first startup tests of the engine. They'll certainly be used for the balancing trials that we're going to do on the gas generator over the next few weeks. So really pleased to have those here. And to finish off the sort of turbine development process now for the blades itself, the one remaining area that we've got to tune now is the grain size in the casting. So that's set by the rate at which you cool the liquid metal as it solidifies and how much time you give these crystals to grow. So at the moment we're a little bit small, which means we've got higher tensile properties and lower creep properties, and we just need to grow those crystals a little bit bigger so that we've got the balance just where we want it for design. But it's perfectly adequate for what we were doing for testing. So turbine blades are in a really good place. Let's have a look at some of the other components that we've got going through the lab at the moment that make up the rest of the engine. So this is the front stub shaft. So this is the very first part of the gas generator rotor. You can see the Curvix at the front of it here, and then the labyrinth seals that make up the shaft. And this is basically the most accurate part that we've ever made to date. So it's a really, really good component. Then we've got the intermediate stub shaft here. This one connects to the back of the compressor and then onto the turbine disc. This has had its first op done here at the front end, and then that's just been inspected, and then it goes back on the machine to have the rear Curvix cut on it and the back end machining. And then we've got the rear stub shaft, and this fits on the back of the turbine disc and then picks up the rear bearing in the spring bar damper there. And then finally, this is one of our cast blades that's had some of its machining and grinding finishing ops on it here. And this is an example of one of the blades that I just told you about that has had all of the metallurgical testing done on it and come back with mechanical properties that are as good or better than we need. That is a Hill cast turbine blade that meets all of the mechanical properties that we require for the engine. Let's move on now and talk about the HX50 rotor blades. So here we've got our rotor blade tooling. This is blade prototype number 4. And what we're doing here is just refining the detail of the laminate kits that go into this and refining the internal pressurization we use during curing to get that internal spar formed just right with proper consolidation and making sure that the foam core that fills the trailing edge is held just in the right place. So we've got all the upper and lower skin plies down, we've got the reinforcements down at the root end down. Over here you can see the foam cores being wrapped, and then right on the back bench here we've got the mandrel, which is the spar of the rotor blade, fully wrapped, bagged and being consolidated as we speak. So we're just waiting for the final bits of the foam core that go in the tip of the rotor blade to be machined. They're currently on the gantry mill at the moment being finished off, and then all of this can be dropped into that tool and we should be curing this either tomorrow or Friday. So to date, the testing that we've been doing on the rotor blades has very much been focused about making sure after the curing process we've actually got the carbon and the constituent elements of the blades exactly where we wanted them in the mold so that they develop the right structural properties to give the blade the properties that we want. Now that we're fairly happy that we're doing that more repeatably, we're expecting good results from blade 4. So before we do the cut up on blade 4, once it's cured, we're going to make a start on the structural testing of this. So we're in the process of putting together a range of mechanical test equipment to initially test the mass and the center of gravity, both in the chordwise and the spanwise direction. Then we'll be testing the flapwise and edgewise stiffness of the blade, the torsional stiffness of the blade. We'll do a wrap test to look at the natural frequencies, the modal shapes, the modal inertias, and then we'll start looking at some of the impact characteristics of the blade, so the robustness of the trailing edge to impact damage, the robustness of the bonding from the skins through to the core to impact damage, and then some residual strength testing on what's left. Once we've done that, we can then cut the blades up and we'll do a detailed geometric inspection to validate that we are indeed getting the material where we want it and that we've got proper consolidation throughout, so we've got no pores or porosity in between the layers so that the blades are starting to develop the full strength that they're designed to. One of the key things that Blade 4 will allow us to now do is to carry out some very detailed structural testing, so strength testing of the blade. We can do structural testing on the pull-out strength of the lugs that are built into the end of the blade that support the blade to the rotor head. We can look at three-point bending to understand the strength that's developed in the lifting portion of the blade, and a bunch of other things. Importantly, that will then allow us to develop the tool chain for predicting both the aerodynamic performance and the structural loads that are developed in the rotor blade, and to corroborate that against our finite element methods as well. So not only does this blade validate that we can make blades, it allows us to prove physically that the blade produces the level of strength and stiffness and mass distribution that we need for the dynamics, but it also allows us to prove that our predictive methods do exactly what we think they do. Let's move on now to the DigiCockpit. Our primary goal for the end of the year for the DigiCockpit system was to have essentially flight viable prototype units ready to go into the prototype aircraft. So what that involved is flight ready screens for both the PFD, the MFD and the IPI. This has got the 1000 candela light box on the back. It's got the touch glass, all of the relevant coatings and the right screens and resolution. We've got those in place now. It also includes the mechanical packaging that goes around the screens to package the primary display processor, the secondary display processor, and all of the interconnectivity that's required to link the screens, the IPI, and all of the peripheral systems. All of that's done. The primary flight display board and the secondary display board, all of those are being populated at the moment. They're being manufactured right now, and we're expecting to receive those in the first week or so of January. So that's essentially on target as well. In addition to that, obviously we need the hardware and the software to be completed. So Eric has studiously developed what we're calling version 1 of the production grade DigiCockpit. So that's the full user interface for the PFD, the full user interface for the MFD, and the full user interface for the IPI, all developed out in a way that is robustly certifiable. All of that has then been integrated with each of the peripherals that you've seen us testing and developing on the bench here. So the primary display processor can now control all of the things like the COM radio, the transponder. It can communicate with the AHRS and with the GPS source and everything else that it needs here on the loom. All of that's now tightly integrated. Those systems are working. So the very next step for us is to get that first prototype hardware, port all the software onto the prototype hardware, connect all of this stuff up, and then systematically work through these things to validate each of these functions work properly. Once we've tested the flight hardware, there's 2 remaining outstanding tasks to do. The first one is to develop out the reversionary display, so to implement that on the target hardware with all of the detailed graphics implementations we need there. That's a relatively short task. And then the second task, which is a slightly bigger job, is to finalize the implementation of our safety monitor algorithms on the target hardware. So these are the algorithms that go and check that the information that's being displayed to the pilot is exactly what came out of the AHRS and all of the other high integrity sensor systems. So it makes sure that what you see is reliable. If it's not reliable, it turns off that display unit and gives you the lower graphics but higher integrity reversionary display. That's the work that will go on into next year. But once we've got this hardware, once we've got the hardware here and tested, we've got something that's good enough for us to do the prototype flying. A couple of quick updates now on the airframe, starting with the seat. All of the structural optimization and analysis that we'll eventually need for certification and approval has now been done. Everything that can be done prior to test has now been done and completed to that level. The guys are just finalizing the reports, and while they're doing that, all of the components have now been released to manufacturing. So we've got the composite components going through the shop at the moment. So we've got the tooling for the carbon bucket, the headrest, and then the rear panel being produced at the moment. We'll take you down and show you those in a second. The mechanical components, the seat legs, the slider rails, the adjuster details, and then all of the componentry associated with the energy absorbers is starting to work its way through the machine shop now. We're making 10 seats to work our way through all of the structural, static structural load cases we need to, as well as the eventual crash test as well. And that includes both the floor mounted seat for the front and the bulkhead mounted seat at the rear. In parallel with that activity, we're developing the production variant of the seat cover. So that's essentially out with a partner company at the moment that's doing some of the trim development for us, and they're looking at Gucci little features like how we do the embossing on the center of the seat cover of the headrest, the stitch details, the perforations, and all that fun stuff. We should get the first one of those seat covers back here on Monday so that we can have a look at that with the rest of the seat assembly. And then on from that, it's literally to detail out the test plan, and we'll be on with testing early in the new year. So in addition to the seats, we've also now finalised the new mechanical design for the door handles, both for forward, rear and cargo doors. We've dramatically improved the situation, adding a separate handle here to allow you to open and close the door, and a much smaller and more elegant internal door handle, with all of the gracefulness of the external handle being retained with an improved key barrel. The mechanism inside has moved from a single point to a 3-point locking mechanism, and all of that stuff's now been detailed out. And we've got all of the integration of the central locking and all of the associated systems with that developed out and neatly packaged within the door. This is the pattern that allows us to make a carbon fibre mould for the rear skin of the carbon seat bucket. So this has got the structural beams in there, it's got the details for the ribs in the back of the seat, it's got the seat belt mounting points, and then all of the structure that you need for all of the associated hardware that has to be connected to the seat bucket itself. We'll take a carbon mould from this, and then between the two carbon moulds we can make the foam core seat bucket. This is the forward half of that, so this is the tool for the forward skin mould, and this is one step further beyond that one. So what you can see on here is we've currently got under vacuum the actual carbon fibre mould on the pattern that makes these components. So that's going through consolidation at the moment, and then that can be pulled off and cured. 2025 has necessarily focused on building GT50. We had 50% of the components of the engine on the test bench by the end of Q1, and we now have 70% of the remaining components in manufacture right now. Despite widespread skepticism, we produced our own bearings to class-leading tolerances. We produced our own aerospace-grade gears. We produced high-quality, accurate, precision fabrications from superalloy materials. We machined compressors and other turbomachinery components. We cast our own turbine blades to the required mechanical properties right here at PC1. And then we've balanced these complex assemblies to incredible tolerances to make sure GT50 can run smoothly and without vibration. In 2026, we'll leverage all of this groundwork to move from making these components to testing these components, and GT50 will finally earn its stripes and bring the whole business model and company to life. As we test and approve the GT50 engine, our focus and reporting will turn back to HX50 as we ready that for prototype production, ground testing, and finally flight testing. There's no escaping the fact that vertically integrating the entire aviation supply chain to allow us to cost-effectively develop both a gas turbine engine and an aircraft has been an enormous task. But we've done it, and now it's time to test. Thank you for all of your support and patience during 2025. Next year is going to be an amazing year, and the whole team cannot wait to get this engine on the test bench. Have a great Christmas, a great New Year, and we'll speak to you in January.